So today it'll be the TA Nilesh who will be teaching this lecture. So Nilesh, you can go ahead.
Thanks, Indrajit. So, yeah, today's lecture is on Introduction to Deep Learning. Here we'll talk a little bit about deep learning, what it is, why do we want to do it, and what are its applications, why is it so exciting? And then we'll look into what are the key ingredients that make this deep learning framework. So, yeah, let's begin. So, what is deep learning? Deep learning is a subfield of machine learning that leverages deep neural networks to model data. So if we draw a rough Venn diagram, so like if AI is the bigger uh, circle, like which constitutes of like the goal of trying to mimic human behavior, like trying to mimic human intelligence. So machine learning is a subfield of AI which uses statistical techniques to sort of do AI. Uh, Deep learning is a smaller circle inside machine learning, which specifically leverages neural networks to achieve the goal of AI, which is trying to mimic intelligence artificially. So why do we want to do it? Like why not traditional machine learning that we have seen so far? Because it is a very powerful technique which allows us to automatically learn representations from data, eliminating the need for manual feature engineering. That is like with classical machine learning, there are oftentimes like you need specific practitioners in the field to design the features for the task that you are solving for to get an effective method. What deep learning promises, not like sort of promises to do, is it eliminates that need, and it can learn from large amount of data by itself without any need to design features or like special representations to enable machine learning. So, deep learning, neural networks as a concept have existed before. Like have, they were first introduced in something like 1950s, but they were not successful at that time. In this current, like since last decade, they have gained a lot of traction, and this has happened because of these three components. First is the hardware, that is GPUs and TPUs happen, which are a very powerful hardware to accelerate these matrix operations. And then like internet also happened, which gave us a lot of data to train on. So these unsupervised methods, which don't need uh, uh, any any annotation to train on, they became possible because like the data was so much available that like you were able to train on such a vast amount of data, and the model was able to learn properly. And then the third pillar is the frameworks. These it is sub frameworks like PyTorch, TensorFlow, JAX. They provided a very seamless APIs to work on and to share code on that open source community could build upon. And a lot of the details of the deep learning could be hidden inside these frameworks, and people can work on abstractions, simpler abstractions. So these three pillars kind of enabled deep learning in modern era. So let's come to some of its applications. So essentially any intelligent task can be deep learning can be applied to. It could be object recognition, that is given an image or a video, like you want to identify an object. It could be self-driving. It could be playing games, something like chess, AlphaGo, Go, and any kind of games. Like recently, a AI agent has also solved Among Us, which is great to see. And conversation agent that we see as chatbots, like they are ubiquitous these days. And then we have media generation, something like Imagine, DALI, and much more that followed, which can, like, given a text prompt, they can generate an image or a full length video, even these days. And at the end, like maybe like the any like the artificial general intelligence, that probably, like at least that's the goal that we want to solve using deep learning. So all of these applications are exciting, and they are worth working for. So let's look at like some of the key components of deep learning. So there are three kind of broad components of a deep learning framework. The first is the model, which is typically a neural network that maps your input data to output prediction. Then second, you have a loss. It's loss is a scalar quantity that defines how well a model fits our data. So it is typically defined using a loss function, which consumes your model and your data, and it gives out this scalar quantity, which we call loss. So the third is the optimization. It's a process, typically some variant of gradient descent, that adjusts the model parameters to minimize the loss. So it's essentially the learning process, that you have defined your task and you have defined your mechanism to solve the task. Now, how do you learn? The learning process itself is what we call optimization. So these three are the key components. And in the rest of the class, like we will dive deeper into all of these three components one by one. So before we go ahead, any questions so far? Okay. So let's come to the model, which is essentially neural networks in the case of deep learning. So a brief history, like I said earlier, the early work on perceptrons in 1950s laid the foundation for neural networks. But back then, because of limited compute, limited data, these methods were not that successful. And eventually, like the excitement around these methods like did die down. But in 1990s, like they saw a resurgence, and with more data available, and specifically in 2012 with ImageNet and GPUs getting available, like they saw a big rise in popularity, and that's the main it's been the main like workhorse behind all kind of AI since then. So roughly it's modeled after the human brain's neurons. That is, like in the brain, like we see these interconnected neurons where a neuron is a basic computational unit. It takes some inputs and produces some activation based on what kind of inputs it's seeing. So essentially, like it's neural networks themselves are also somewhat inspired. Uh, but they do work quite differently than actual neurons. So it's only fair to say that they are inspired, but they are not exactly trying to replicate what brain neurons are doing. So so let's look at what a neuron looks like in a neural deep neural network that deep learning uses. So it's as I said, like it's the building block for our neural network. um, it's a basic computational unit. So there are four components to it. One is like the inputs. It receives multiple scalar inputs. And then there are weights for each of the input it receives. The weight essentially measures how much that input is important for activating this neuron. And the summation, so like the summation part is just it's doing all the sum of adds up all the weighted inputs that it is seeing. And then there is a non-linearity, which is a filter or activation function that given given the weighted sum, like it decides whether to like shoot up or like stay below zero. So it's acts kind of like a filter function if you want to loosely draw analogy. So let's quickly look at like a basic neuron. Um, Here, like I'm looking at a linear neuron. This doesn't have non-linearity. So it just is doing a weighted sum of its inputs. So here as like we have our input, sorry, our input consists of, this is our input, which is a two-dimensional input. First is x1, which is your x coordinate, let's say, and your x2, which is, let's say, your y coordinate. And here, like all throughout the figures, the kind of notation is like blue represents a positive quantity and orange represents a negative quantity. So keep that. And like if you are uh like sometimes like when I'm like denoting data points like or like classification, so they represent like two different classes. So mm, so like here, like as we can see, um we have this neuron which essentially like is this module. It's taking two inputs, x1, x2. It's multiplying x1 with w1, x2 with w2, summing them up and giving this output. Sorry, which is z that we denote. It's w1 times x1 plus w2 times x2. So that's how a neuron looks like. And on the right, like I have shown the decision boundary that this neuron creates. So essentially, depending on what your W1 and W2, this decision boundary will look something different. But right now, for like for some W1 and W2, the decision boundary looks like this. And it is always going to be a linear kind of a decision boundary uh, because like it's a linear function, the like what a neuron is modeling. And yeah, here you can see that like for this particular data, this decision boundary like perfectly fits the data that we have. So that's what a linear neuron looks like. Now let's add a non-linearity in this neuron. So essentially like we still have the same, this is our input, but our neuron now has this additional component, which is our non-linearity. In this case, in the diagram, I'm showing you a rectified linear unit, which is in short called ReLU. It's a simple function, which we'll see later, but like it's essentially like for all the negative input, like it stays at 0. And for the all the positive input, like it linearly gives you the identity function. So this is our x-axis, this is value of x. So it's a very simple nonlinearity that is like it just kind of partitions your the input that it is seeing. So if it's negative, it remains 0. If it's positive or like non-negative, it just gives you the input itself. So it's a very simple nonlinearity, but like this itself is very powerful. Like if you will see later that if you start stacking up neurons with such nonlinearities, like you can just draw arbitrary, you can fit any arbitrary function. So I hope so far the the things that I presented are clear. I'll take some time to see like if there are any questions or anything confusing with the notations. Okay. So there are let's take a brief look at some of the non-linearities that are popular in deep learning and kind of constitute the basic non-linearities. So first is ReLU, as I said, like it's a function g of x, which gives 0 if x is less than 0, and it is x if x is greater than equal to 0. So it's a simple function. It's kind of looks like this. And yeah, but it's still quite powerful, and like some variations of it is still used in everything that you like all the top deep learning products that you see, including ChatGPT and stuff. So this is a ReLU nonlinearity. And then sigmoid, as we saw in the last lecture, it, it's the function that it represents is this 1 plus e power minus x. So essentially, like its graph looks something like this. Like for maybe I should use different color. For all the negative values, like it remains at 0. Not all the negative values, but like if your x is very negative, like it kind of stays close to 0. And then at x equal to 0, it gets to like 0.5. And then at slowly it starts increasing, and then at 1, it gets capped at the value of 1, like as you keep increasing your x. So it kinds of like acts as a gating function that um, if your x is very negative, like it is 0. If your x is very positive or like even moderately positive, it gets to 1. And in between, like it gradually rises to 0 to 1. So that's how the curve looks like. This we have already seen in our previous lecture. Tan h is also like it's the inverse tan function, and it's essentially like the same as sigmoid, just that like it's a scaled and shifted version of sigmoid, that it's instead of like being capped between 0 and 1, it is between -1 and 1. So it's almost identical to sigmoid, just that it's 1 -1. So it's kind of like 2 times wider than sigmoid, and like but and the other thing is like at 0, it is at 0. So very similar to sigmoid. Then we have softmax. So softmax is something different than these three nonlinearities. So in the sense that like these nonlinearities are act on a scalar. That is this x that so far I've been giving, it's a real number. But softmax acts on a vector. So here, let me denote the vector with different notation. So here my x is a scalar, a vector of real numbers. So what it does is like it takes a vector and gives you a vector. So it g is my softmax is r to the n to r to the n, and the ith element of this vector is going to be e power xi divided by sum of e power all the xj's, where j is from 1 to n. So it's uh, So it's typically used to convert a raw vector that is unbounded. That is like it can all the values inside the vector can be anything between minus infinity to infinity. And then like it takes that vector and converts it into a probability distribution. That is like if you see that like one good property that this has is like summation of all the gxi from I1 to n is 1. That it satisfies the probability constraint that, and more on top of that, g of xi is greater than, actually is greater than 0. So, and these are the two things that we need for a vector of scalars to represent a probability distribution. So we'll see this often at the output layer of a neural network. We'll talk about like what output layer of a neural network is. But whenever we want to convert some raw vector quantities to a probability distribution, vector of probabilities, then like we use this softmax function. And yeah, this is also something very popular now that we'll see later. Okay, so that concludes the brief discussion on the nonlinearities. Let's see how these neurons can be interconnected to form a deep neural network. So a deep neural network like essentially is a layered arrangement of neurons that that forms a neural network. So for example, in this, like each of like we have two hidden layers, this and this, and then we have the input layer as before, and then like here is our output layer, like which so essentially like there's a neuron sitting here as well, which gives out like just one single scalar. So here we have so all of, remember, like all of these neurons are some like represent just this quantity, just that like they are arranged in a stacked up manner now. So let's look at like how do we how like how does this whole neural network acts as a function? Like how does it take an input and gives you the output that you want? So let me try to write the some notations first. So yeah. Remember that like each of the edges represents a weight. So the as I said, like the notation that here I'm using is blue color represents a negative quantity, blue color represents a positive quantity, orange represents a negative quantity, and the thickness represents the weight of that quantity. So here, like if you see, like these are the weights of your neural network. So this, let me denote as, sorry. Yeah. So this is the weight for the first neuron and the first input. So I'll represent W11. And this is the weight for first neuron and second input, sorry. So I'll represent as 2, 1. And similarly, like we can have like a weight for each of the edges that we see here. So here, like the notation that we'll be using is like because this is for our second hidden layer. So this takes the first input and it's for the first hidden layer neuron of the layer 2. So P2. So if we look at this neuron, which I'm going to call N1, 1, so because like this represents like which layer it belongs to, layer 1. This represents like what is the index of this neuron in that layer. So this N11 has two parameters, which is W1, 1, and W2. Similarly, like if we take this here, hidden neuron, this I'll call N1, 2, represents layer 2, represents index of this neuron. So this has three parameters, which is W2, 1, 1, W2, 2, 1, W3. So as you can see, like all of these neurons comes with their own parameters. So like if you go on to write the whole equations, like it will become quite messy. So how we typically represent uh, our neural network is in terms of matrices. So each layer uh, gets can be represented as a matrix of size, in this case 2 cross 3, because it has like it takes two inputs and it produces like three outputs. So we can represent hidden layer 1, H1, as W1, which is a matrix of size 2 cross 3. And then we can represent hidden layer 2 as W2, which is matrix of size 3 cross, sorry, this case 2. And then we have the output layer, as I said, like imagine a neuron sitting here, this, in this case. So its shape is going to be 2 cross 1 because it's taking two inputs, producing one output. So, and one thing that I missed is there is also like the inputs can also be considered as a layer. So in this case, the input is just one data point, but typically in deep learning, like we deal with uh, multiple inputs at once. So like we create a batch of inputs. So in this case, let's say the batch are like in the batch, like we have only have one data point. So like our uh, input is of shape 2 cross 1, where this 1 represents like the batch size in this particular case, but it could be anything. So this is our X. And now if we go on writing our like what function this whole neural network represents, so we can write that. So the can write Z1, which is just the weighted sum after hidden layer 1. That's going to be so let's see the shapes. It's so we want to have like 3 outputs, and we have 2 inputs. So it's going to be if someone wants to help me, like in what's it's going to be like W times X, but like, does anyone, is this right? Like just writing W1 matrix multiplication with the X? No, right? Like the shapes don't match. Sorry, someone was saying something.
Yeah, so should it be X transpose times W?
X transpose times W also works. It depends on like what kind of notation you want to use, but like it does work. It will, like if I do X transpose times W, this will give me something of the shape 1 cross 3, where like I've shifted the batch axis on the first one.
Right.
And here, like this is my output axis. Or I could have written, instead of this, I could have done the other way, like without shifting the batch axis, which is W1 transpose X, which will give me 3 cross 1, where the batch axis remains consistent.
Right.
So for the sake of this lecture, I'll use this notation, which is like I'll use W transpose X to denote the linear combination. But yeah, you could have done X transpose W. It just depends on what notation you want to use. So this is my, so, but remember, like this is not the final output of my hidden layer 1. This is just the weighted sums. I now need to apply the activation. So let's assume that like in this neural network, we are using sigmoid activation, which we represent by sigma. So our, maybe let me use a different color. So after applying the activation, we'll get sigmoid of Z1. And this is an element-wise operation, so it doesn't really change the shape of your output. So it still gives you a 3 cross 1 entity. So, and now this A1 is what this whole output that we will be seeing from the collective 3 neurons in the hidden layer 1. So, okay. So now that we have seen like first layer in action, we can now see second layer. So the weighted sum of the second layer is going to be something like W2 transpose. And now remember, like this hidden layer 2 is acting such as like the output of hidden layer 1 is input for hidden layer 2. So now we'll multiply this with A of 1. And what's the shape that I'll get? I'll get the shape, since it's W2 transpose, I'll get 2 cross 1. So remember, this 1 is still my batch axis, and this 2 is the output that I'm seeing from hidden layer 2. And finally, like I can, like similar to hidden layer 1, I can do A2 as sigmoid of Z2. And then let's assume that there is another neuron which is of size 2 cross 1. So my Z3 is going to be W3 transpose A2, and assuming this also has the sigmoid activation, this is going to be sigmoid of Z3. And what's the shape of this? It's the 1 cross 1 batch. So that's the final output that my neural network is giving me, like for a batch of data points, which have 2 dimensions as the features. And in this case, there are only like the batch size is 1. So that's why I'm getting a 1 cross 1. But if I had n data points in my batch, I would have got a R1 cross n quantity at the end. And A3 is my final output. And that's how typically a neural network works. So I hope this is clear, and specifically the notations are clear. I did like it's not written that cleanly as I imagined, but yeah, if there are any questions here, like please let me know, because we'll be using this notation and this way of thinking about neural networks later in the class, and actually like later throughout the whole course as well. Okay. So let's come to the question that like, why do we even need this nonlinearity? Like, essentially, like what we said initially was that a neuron like takes some inputs, and then it needs to accumulate those inputs into one signal. So why is the summation not enough? So I'm sure like some of you already know the answer, but still, like if others who don't, like they wanna make a guess, or if the people who know, like they wanna say like what's the intuition behind having a non-linearity inside a neuron?
So we can like model more functions.
But why not, like if I just had like in this neural network, if I just had linear neurons, like why is that not enough?
Because we might have well just used like linear regression. Like we didn't like there's no point in using a neural network if it's just gonna be linear, right?
Yeah, so that's true, that like if you have a bunch of linear neurons and you connect it in any way that you want, you will still end up getting a linear function. And I mean, all of these diagrams that I've been using are from this playground.tensorflow. So let's quickly take a look at like what for this dummy example that we had. Like if we had like bunch of linear neurons connected like in a fairly complex setup in a neural network, and if we did training over it, like anything that we do, like we'll still get a linear separator of data. And particularly for this kind of data, which is a concentric circles, like we won't be able to separate it. So you can try to write the math, and like you will see that like you will at the end the neural network will be like it will just represent a W times X operation. So let's see like what go back. Let's see like if we had a ReLU activation here, and then we did like training of our model, like you can see like it can give you like some, like the hidden neurons here can give you a part, like a kind of a partition of your whole space, and then they can be combined in a way by the later neurons to give you a much more complex boundary. For example, like it's like this is creating like a parabolic shape from the right side, this is a parabolic shape from the left side, and then these things can be combined to give you concentric circles. So if you see, like even with a very simple nonlinearity such as ReLU, like you were able to approximate it, even if you have a sigmoid activation, like that would still give you a similar result, just that like it will, okay. In this case, it's not. Okay. With enough learning, like it does give you. So as you can see that even with activations, like they can be finicky at sometimes. So like depending on the type of problem you're solving, like you'll have to choose the right kind of activations. But like having a non-linearity really helps in modeling complex data. So coming back to our lecture, so non-linearity gives us a superpower that like combination of non-linear neurons is much more expressive, and it is uh, it is actually like so powerful that like it can be shown that a neural network with at least one hidden layer and which has a sufficiently large number of neurons and an appropriate activation function, it can approximate any continuous function um, that to any desired degree of accuracy. So um, I'll give a slight intuition about like this theorem. So essentially, like let's say that like we have this function, this blue curve that we want to approximate. So how we can approximate it, like we can construct a neural network which has like one hidden layer and it has enough number of neurons in it, and it can like approximate this function to an arbitrary degree, to an arbitrary accuracy. And how we can construct such a function? The key idea is that like two neurons can be constructed to give a pulse function. That is like if you have, for example, like ReLU activation, then you can have one neuron which gives you the one side of your step function, the other neuron which gives you the other side of your step function, and you can combine with the weight 1 and -1 to give you this step function. And this width you can control depending on like the what values that you choose for T1. So like typically like there's a bias also like in your neurons, which for brevity I didn't show earlier, but depending on the biases that you choose, like you can shift these uh, activations like left or right, and you can get a very arbitrary smaller width T1 uh, step for pulse function as well. And then like all of these pairs of neurons can be just summed up at the output layer to give you a like a bunch of rectangles like which approximate it. So if you keep like reducing the width of your pulse functions, then like you can like just get to an arbitrary degree of approximation for this continuous function. So yeah, feel free to read more about it, but like it's a pretty neat construction and pretty powerful way to see that like with just like simple non-linearities, like we are able to get something this complex. So yeah, I realize like I'm running a bit short on time, so I'll speed up a little bit. So now, but still, like any questions so far? Okay. So coming to loss functions. So like remember like how we started was deep learning has three key components. One is the model, then is the loss function, and then is your optimization process. So we have seen the model so far, which is a deep neural network and how we do computation with it. Now let's come to the loss function. So loss is essentially a measure of how good our model is for an input. So usually it's quantified in a negative way that like we measure like the cost of an incorrect prediction. So like if your loss is 0, then your model, if your loss is less, then your model is better. So it's simply a notation or like a convention kind of a thing. You could have defined it the other way as well, but like it makes things like mathematically like easier to justify sometimes. So so again, like it's a scalar measure of how good our model is for an input. So typically in deep learning, we measure the empirical loss, which is that we measure the total loss averaged over an entire data set. So let's say like we have like n data points, then like typically our loss is going to be 1 by n summation over I to n, and the loss function, which takes your model parameters, which I'll represent by theta, and your ith data point, which I'll represent by xi, and then you sum over your all of your entire data set, and then you take the average. So this is what we call empirical loss or empirical risk. So we have seen loss functions like in so far in the lecture. The first one that we started was a regression loss function, which was mean squared error. So here, like we are given like our yi is a scalar that we want to approximate. We make a scalar prediction, which is our yi hat for the ith data point, and we take its the squared difference as our loss function. So our like small l is going to be just the predicted scalar minus the actual true scalar squared. So this has we have seen this already in regression. Then in the last lecture, we saw binary cross entropy for doing logistic regression. And this is essentially like we had a two-way classification problem. That is like we want to identify whether this class is present or not. So our yi is 0 or 1. And then like yi hat is the probability of class being present, which is given by your model. And then like our loss is this quantity, actually the negative of this quantity, which I've taken here outside. So the negative of this quantity is our loss for that data point. And this we call the binary cross entropy. And remember, like this works for a kind of a two-way classification problem. That is, you want to identify whether something is present or not. So like a generalization of this binary cross entropy is the cross entropy function, which if you like really look deep like carefully, like if you have it looks very similar to the binary cross entropy. It's just a general version of it. So this is for like if we have two like instead of two-way classification, we have C-way classification problem. That is, we have like C classes to classify into. Then we can write our loss like in this way. And if c equal to 2, you can see that like it will actually will be the same equation as the binary cross entropy. So this loss is typically like remember like here like our yi hat is a vector of size c. And this yij hat needs to be a probability distribution. So like typically in deep learning, as I said, like whenever you encounter a probability distribution, you model it using softmax. So this yi hat is often or like almost all the times like a result of a softmax operation. So its cross entropy is like very much like if you in deep learning, you'll see like it is paired with your softmax operation. But this is the loss function. Like if you have a C-way classification problem, let's take a look at some examples and see. So for the first example, we have this input of an image of a cat, or like it may not be a cat, and that's our task. That is there a cat in the image? So what kind of loss function will you use in this case? I know it's simple, but still feel free to speak up.
Would you use binary cross entropy?
Yeah. So because it's a two-way classification problem that we wanna identify if a cat is present or not, like the right or the appropriate loss function for this task is going to be BCE, which is binary cross entropy. So let's take another example. Like let's say like we want to determine the age of the cat. What loss function like should we use now?
Mean squared error?
Yeah, because we wanna like our output is now just a scalar quantity, so we can use something like mean squared error, like to do regression over it. Also, like it can potentially be solved using cross entropy as well. Like we can just model every age category or every age that exists as a separate class and do it. But in this particular case, I don't think it's the right formulation. Yeah, but I just wanted to say that that can also be used, but a mean squared error is the more appropriate option in this case. And then like it could be that like we it's not just a one-way classification, two-way classification, that means there is a cat or not. Let's say we want to determine a cat versus a dog versus a bird. So this becomes like now a three-way classification. So for this, cross entropy, specifically cross entropy paired with softmax, is a appropriate uh, loss function for this task. So, okay, any questions so far? Like, because now we'll be moving to the next component. So coming to the next component, which is optimization. So remember this, here we'll be talking about optimization on a very broad level. We'll have like a specific lectures dedicated to optimization and the better versions of optimization we can do. But here I just wanted to introduce optimization in the context of deep learning and how does it like look like on a broad level. So the overview of optimization is the goal is that we want to minimize the loss by adjusting the model parameters. So let's say like our loss surface looks something like this. In this particular case, we only have two parameters, W1 and W2. And for each choice of W1 and W2, like we can like have a loss for W1, comma W2. And let's say we have some data D. So this loss will be a scalar quantity. Sorry. And this is what is represented on this axis. So for a particular choice of loss of W1 and W2, we can get some loss here. So if we draw the whole loss surface, it will look something like this. And the goal of deep learning or goal of the whole ML process is to get your some model parameters which minimize this loss, which gives you the global minimum of this loss. So like one very brute force thing that you can think of is like you can just try bunch of random W1 and W2, or maybe a grid of W1 and W2, and then evaluate your loss on each of those choices, and then you can choose the one which gives you the least loss. But of course, like even in this case, like where we only have two parameters, like the search space is pretty big because like it's continuous. So even then, like this brute force approach might not is going to be infeasible and will not give you the right results that you're looking for. But typically, like in deep learning, like we easily have billions of parameters these days, or like even touching trillion of parameters. So in that case, like it just becomes like infeasible to even think of something like brute force. So we use like the most popular optimization process that is being used in deep learning is gradient descent, which is like we iteratively update parameters in the opposite direction of the gradient. So we start from a random initialization of our W1 and W2. Let's say this point is here, and then we compute the loss, compute the gradient with respect to W1 and W2, and take the step, like a scaled step in the opposite direction of the gradient. So the scaled opposite direction will look something like this. Here it's denoted in the picture, but maybe it's not very clear to see. So, and we keep taking these steps again and again. And this will eventually, like for some loss surfaces, it is guaranteed to arrive at the global minimum. But even though like it's quite surprising, and it's one of the probably unknown parts of deep learning, is that like even like currently in deep learning, loss surfaces don't look this smooth or this neat. Like they are very jagged, lot of filled with a lot of valleys and um plain areas. But still, like this gradient descent works, like or like some version of gradient descent works, which is just the simple process of iteratively updating parameters in the opposite direction of the gradient. So that's the kind of the overview of gradient descent. If we try to look at in terms of an algorithm, the pseudocode would look something like this: that you initialize your parameters, your W weights randomly, or like from a like some distribution, and actually like how you initialize your parameters also play a role in modern deep learning. So this will, like in one of the homeworks, will take a look, like it will you'll experience that like with different initializations you'll get different results. But in this lecture I'm not going to cover it. But you initialize your parameters. For now, let's just assume like you're initializing randomly from a normal distribution. And then for like until convergence, for each iteration, like you want to compute the loss L. You want to compute the gradients of the loss with respect to each of your parameters that you have. This will give you your gradient vector, and you update your parameters by a scaled negative of your gradient. So this eta is our scale, which is typically the learning rate. And this negative dl by dw is our gradient, the negative gradient. So that's the pseudocode for gradient descent. But okay, so I mean, like the algorithm looks simple, and all of these steps, like initializing parameters, like we know, like we can do call np.rand, computing the loss. We saw that like we can do like how to do a forward pass with neural network, and then like you just need to plug your loss calculation equation there. This also like looks simpler. Like once we have dl by dw quantity, then like this is just like one equation which can be just written in one line. But this the computing the gradients of the loss with respect to w, this is the one of the hard parts of this algorithm. And that we achieve like in case of neural networks, or in case of like any kind of functions, like continuous functions, we can do it like we need a efficient way to compute the gradients for all parameters. And we do it using via backpropagation. And it is backpropagation is essentially like the chain rule to like propagate errors starting from the output to the input. So just a refresher on the chain rule. So like chain rule, like for a parameter theta that affects the loss L through an intermediate variable Z, we can write del L by del theta as del L by del Z times del Z by del theta. So that's your chain rule. And like back propagation typically involves like a forward pass and a backward pass. Forward pass is the what we already saw, that like in neural networks, like how to compute the final output of your function. So forward pass just means like um, along with computing just the final output, you also compute all the intermediate activations as well, because that will be needing in the backward pass. So you compute all intermediate activations, ZL and AL, that we saw earlier. And then like in the backward pass, starting at the output layer, you compute the gradient and propagate it backwards. So, I mean, I know like here I'm just saying it, but let's take a look at a sample task and how to do back propagation on that task. So let's take this sample task that we saw earlier, that like it's a concentric um, uh, classification problem. Like you have like your orange data points on your outer ring, and then you have like the blue data points in the inside, and you want to classify orange from blue. So maybe like something you want to get like a boundary like this. So here, like let's say like because like it's a two-way classification problem, we'll be using the binary cross entropy loss function. Sorry, there should be a negative here. So, and the model that we'll be using for this sample task is going to be a neural network with one hidden layer. There's only one hidden layer, H1. And then this is my output layer. And this is my input layer. And we will be using sigmoid activation. And there are like 3 hidden neurons in my activation. And in my hidden layer, layer 1. So the optimization process, as I showed earlier, like it will be the gradient descent method that will compute the loss, compute gradients, update parameters. But as we saw, like this is the hard part. So that's what we'll be diving a bit deeper into. So the forward pass, let me write again, like we have already seen this, but for X, we can define as a matrix, which is of 2 cross 1. It has 2 features and 1 data point in this case. And then our H1, which is parameterized by W1, is going to be a 3 cross 2 matrix. And then my output layer is going to be W2, which is 1 cross 3. And my forward pass is going to look like my Z1 is W1 transpose X. My A1 is going to be sigmoid of W1 transpose X, or let me just write Z1 here. My Z2 is going to be W2 transpose A1, and my A2, which is also my final prediction from my neural network, so I'll call it my Y hat as well, is going to be sigmoid of Z2. My loss function is going to be here, because there's only one data point, so I'm just writing it for that. It's going to be Y times log of Y hat plus 1 minus Y times log of 1 minus Y hat. Negative of this. Any questions so far? So this we have kind of already seen, like we have seen a more complicated version of it. Right now there's only one hidden layer, so it's simpler to write. So that's what my forward pass is going to look like. And remember that like I'm along the way, I'm storing my Z1, my A1, my Z2, my A2, because that I'll be needing in my backward pass. So, okay. So let's see like how the backward pass looks like. And for this particular demonstration, we want to compute our del L by del W1, 1, comma 2. That is for this particular weight, W, comma 2. We want to compute the gradient with respect of the del L by del this weight. So as I said, like let's try to draw our chain. Like we have our X that using W1 using W1 we got to Z1, using sigmoid we got to A1, then using W2 got to Z2, then using sigmoid we got to our Y hat, which is also A2. Then like applying our loss function here, like the BC loss function, we ended up being at L. So we want to get del L and by del like W1 comma 2 is part of this matrix. So like we want to like go backward in this chain. So does anyone help me get like or like just want to say what this chain rule is going to look like?
Nilesh, I think the slide is stuck on the optimization forward pass.
Oh,
Okay, so somehow, yeah.
oh, I didn't realize this. Sorry.
Maybe like
Okay, you can see the slide now, right? Like, and does anyone help me write the chain rule here?
maybe like DL
Mm-hmm.
over DY hat
Over dy hat. Okay.
multiplied by DY hat over DZ2. And basically, yeah, you just keep following like the chain, like the diagram that you drew out, except backwards. So the next one would be like DZ2 over DA1.
Right. We can keep going backwards. Should have written it more neatly. Yeah, so that's what your chain rule is going to look like. And specifically because we are kind of just like in this particular example, we are just looking at the W1 comma 2. So we can kind of further simplify this into like not all the parameters in our Z1 is going to get affected. Like as we can see, like there's like just a single chain. So like we can simplify this into del L by del Y hat. Times del Y hat by del C2.
Are you writing, Nilesh?
Yeah. Oh, you can't see?
Yeah, somehow, okay.
Okay. Oh, I don't know.
I don't know why there's a lag.
I see. Sorry about that. Del C2, we can see that only the second component of A2 is affecting it. So like we can just write here, like del A1 2. So, a little bit messy, so I'll remove this part. Mm. So I've just like simplified it for this specific weight value that we are seeking. So like here I just like written the specific coordinates which are going to affect this quantity. So I don't have too much time, so like I'll just like quickly go over it. But let me. So this quantity, if you simplify for the binary cross entropy loss, this will turn out to be a very simple quantity, which is going to be your y hat minus y. This whole quantity, and then del z2 by del a12. As we saw, like it's like how they are related, like A12 is kind of it's like we multiplied A1 with W2 to get Z2, so that's why like it's only going to be like if let me yeah, so my Z2 was W2 transpose A1. So that's the relation between Z2 and A1. So this quantity, if you compute, this will turn out to be just W2 and the second coordinate of W2 and this quantity, like because like the relation between this is the sigmoid activation, so this will turn out to be the derivative of sigmoid. Sigmoid derivative is sigmoid value times 1 minus sigmoid. So I'm just using this property to quickly write the equation here. It's going to be A1 2 times 2, and this again is just this Z1 was W1 transpose X. So this will turn out to be just the second coordinate of my X element. So dot X2. So that's what your gradient will look like. For this particular weight value. And here, like I have shown in just like for this particular W, but in practice, like as in forward pass, as we were dealing with matrices and we had this compact representation, we also like even in backward pass, we like compute the gradients like in a matrix way. So like for the whole weight vectors, we compute simultaneously using matrix operations. So similar to the forward pass, like it's going to be like all the scalar values will get replaced by your matrices or the intermediate vectors that you got. But that you will have to do like in your homework. So like you can get an idea how to do that. But for brevity, like here I have just like explored like how to compute gradient for with respect to one weight value. So that kind of ends like our the full algorithm, deep learning algorithm on a high level that we set out to describe in this lecture, which is like the step one is your forward pass, you compute activations. Step two is your loss computation. You use your the output of your neural network to compute the loss. Then you do the backward pass using back propagation, and then you do the parameter update according to the gradient descent update rule. And you repeat this process for multiple steps until convergence. So uh, in practice, I just want to like take 1 minute to quickly just say that like there are other things that you wanna like you need to incorporate into a successful deep learning algorithm. That is one thing is like efficiency. Like right now, like gradient descent operates on a like the full data set, but that is going to be inefficient. And in last lecture as well, like we briefly touched upon it, that like we wanna do a mini batch version of gradient descent to gain efficiency and better convergence. This will explore later in the class. And then also like the learning rate, we didn't really talk about the learning rate in the gradient descent method. So, and that is also something you don't want to keep constant. So, like there are like adaptive versions of your gradient descent, which depending on the kind of loss surfaces that they are seeing, they adapt their learning rate or their scaling of your gradients based on like what kind of loss surface they are operating in. This also will explore more in the optimization lecture coming ahead. And then there is regularization that we saw in our previous classes. But here, in case of deep learning, regularization will look something different. And this also will explore later and in rest of the homeworks.